Welcome to Base 58's free online lecture about, what are we talking about today? Today we're talking about encodings. We're talking about Endianness, which is sort of, but not really related to encoding, so not really, etc. And then the last thing that we're doing is, the last thing that's kind of fun to talk about, this is actually a type of encoding, is I thought it'd be sort of fun to explain what base 58 is, mostly because that's the name of the class. Name of the class, or I guess name of the school rather. And also because it is the encoding that we use in Bitcoin a lot. Well, used to. We can talk about that when we get to it. Okay, cool. I'm hoping my audio is working. The little bars are popping up. Are the little bars popping up?
Yeah, we can hear you.
Okay, great. Okay, cool. Thank you. Okay, great. Yeah, so let's go ahead and get started. I'm assuming that most people, for the purposes of this lecture, are pretty new to kind of bit fiddling, as we're going to call it. So I'm going to start basically at the beginning with kind of like, how's encoding? How does it work? What's the general idea behind an encoding? Why do we have encodings? What are some different types of encodings that you encounter, especially in computer sciencey things? And then we'll talk about the ones that are pretty common in Bitcoin. Common Bitcoin encodings. Okay, so first of all, what does an encoding mean? So what is an encoding? What a great question. General idea with like an encoding, I think, is it's basically a way of taking some normal information, like let's say, and for all of our examples, we're going to use numbers because numbers are information, right? So if we wanted to tell someone, so we want to tell someone the number 5, for example, we're going to use this, and you could tell them the number 5 out loud, but because this is like a, how to explain it, because we're dealing with computers, right? These are computer systems. Everything's going to be written down. So everything will be written down. So typically, if you want to tell someone in a way that's written down, you tell them the number 5, you would send them a character, a single character that looks like this, right? So if I sent you a message on like chat or something, and I put a single character, so this is just like one space, you can kind of see my cursor is highlighting the number 5, it's like blinking on top of it, takes up one space. This character 5, this little symbol is a way of communicating the number 5, right? So encodings are just ways of taking information like the number 5 or the number 10, and it's how we like write that down and express it. And then basically, like when you send it to someone else, then they are able to like take the characters that you've sent them and make them make sense on their end. So encodings kind of rely on shared understanding on both ends, right? Of the encoding that's being used, sort of like a shared understanding of what character set is being used, right? So if, let's say there's some weird language where, I can type, I promise, where the character, let's say Y meant 5, right? Meant 5 as we're used to it. Then if I didn't tell you I was using this weird language where Y meant 5 and I just sent you a Y, you would have no idea how to interpret this information that I sent you, right? So most encodings are pretty well understood across whatever. Sometimes you'll send someone a number or something, they'll be like, okay, how is this encoded, etc. And then once you have the encoding, you can translate. The other cool thing about encodings is you can translate between one encoding to the next. So, and the reason you can translate between them is much like in languages, the information that's in the encoding, so like the number 5, right? You can say this in different languages, a bunch of different ways, and all the different ways you can kind of like, once you know how to, what language you get the 5 in, you can translate it between other ones. Okay, I've talked a lot. Maybe like an easier way to explain this is to actually just hop into an example. So place I like to start when we're talking about encoding. So the first thing, there's already a code. So good news is there's already an encoding that you are familiar with. That it's the name of the encoding is decimals. So we're talking about right now, and I think for the rest of this thing, unless something pops up that I am not aware of, we're going to be talking about how to encode numbers. Okay, encode numbers. So what are the different ways we can represent numbers and say the same thing, but just in different ways? And then we'll talk about why we say them in different ways and why that's like, why that's useful at all in a second. But okay, so the first encoding that everyone's familiar is decimals. Every encoding, so encodings types, there's decimals is a type. Every encoding type has like a certain kind of feature set about it. So decimals has a how many characters, so to speak, are in the decimals encoding. Does anyone know the answer to this? I'm going to give you a hint. There are 10. What are the 10 characters in the decimals encoding? I'm gonna, so we're talking about numbers, right? So there's 10 different things. There's 0, there's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8, there's 9, right? That's 10. So there's 10 characters, right? If you count these, so character, as we explained earlier, is a, I don't know, number or like, you know, so this cursor, like where my cursor is one character. So there's 1 character, there's 2, there's 3, there's 4, etc. So there's 10 characters. So decimals has 10 characters. Is there anything else I need to tell you about this? I don't think so. Okay. So there's 10 characters, and then just for giggles, I'll put them here so we can see them. Oops, that's fine. So there's 10 characters. Okay, so sometimes things are more easy to understand when we compare and contrast them to different things. So we have decimals. Another one that we have in computers, and one that's pretty common in the Bitcoin class that I'm going to be teaching, is hexadecimals. So hexadecimals are a little different from decimals. The biggest difference between hexadecimal and decimal is the number of characters that exist in it, right? So these are both, I'm going to call them, these are all, let's call them counting systems, right? Because they have to do with numbers. There's 16 characters. What's cool about hexadecimal is that there's 16, right? So there were 10 in hexadecimal. I mean, there were 10 in decimals, and now we're at hexadecimal, and there's 16 of them. So what are the characters in hexadecimal? Well, the cool thing is the first 10 are the exact same as the decimal ones. Let's see. So these, so the first 10 are the same. But what happens once we get past 9? We have to add basically 5 more characters. I have to add 16, 5 more. There's A, a B, a C, a D, an E, and an F. So I added 6 more. So basically, so if I wanted to write out kind of the value of each of these characters, so then each character has a value, right? In decimal, it's pretty obvious what each of these characters, what the value of each character is, right? Because it's one we're really familiar with. So the number 0 has the value of 0. Number 1, like this character here, has the value of 1, right? But in hexadecimal, all of a sudden we have these new characters that we aren't really sure what the value of them is, right? It's not obvious just looking at it. But I can tell you, I can give you a small hint. basically it's going to be, so if I write the same thing, so this is the characters written in hex. If I take the same characters and I write them using their decimal value, right? You're going to end up with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then in decimal, we've run out of characters, right? So what happens in decimal when you run out of characters is you start using 2 characters. So this is 11. This will then be 12. This will then be okay, 13, 14, and then this one is 15, right? Okay, which is pretty cool. Okay, so in hex, we can count basically all the way up to number 15 using a single character, right? So the number of numbers that we can communicate in a single character is the same as the number of characters that are in that set, right? This makes sense. There's 16 characters. So in a single character, we can say we can count up to the number 16. Whereas in decimal, we had to start sending 2 characters whenever we hit 10 characters, right? So basically, by using hex, we're able to, so like the number, so again, just as an illustration, like how do I say the number 11 in hex? Well, I have this handy dandy chart. I can go look up the number 11 and see that it's the character B, right? But then how would I say the number 11 in decimals? I would need 2 characters, right? I would have to have 1, 1. Cool. So the cool thing about encodings and using different ones, and part of why you use different encodings is that you get to save some space, right? So by space, I mean literally like, okay, there's one spot here. I had to send two like runes, I guess, if you want to call them that, kind of like I just send like 2 runes or whatever you want to call them. I've been calling them characters. I just send 2 kind of like pieces of data, like 1, 2 over in order to say 11. But if I had tried to send it in hex, I could have just sent 1, which says B, right? So this communicates the same thing, the number 11, but it does it more compactly. And the reason it does it more compactly is that there's more, I would almost call these like more pre-agreed understanding of what the characters stand for, right? So we've already agreed, because we're using hexadecimal as the standard, there's like already agreement that the letter A, the letter B, the letter C have like a meaning for like a higher value, right? So anyway, so when you're talking in hexadecimals, basically you're able to send more information or communicate higher and bigger numbers in less space, right? So less space that I have to send someone, which is cool. So hex is a good way of expressing kind of bigger numbers or bigger numbers more compactly is kind of the whole idea. So some interesting things is then like, okay, so I can have like a string of numbers. If this was in decimal, it would have a value, right? What's the value of this in decimals? Well, it's whatever I just wrote, right? This is how you would express that number. Let's see, I think that's 10,282,948. So then there's a question of like, okay, how do I write this number in hex, right? So we kind of have like I mean, I could cheat. So down here I have a Python repo. It's just Python. So I could cheat. Python has a way I can take a number. So I can take this number and I can ask Python to calculate it for me. Python gives me back this like we call these strings. It says, okay, that number in hex is this, right? So let's talk about what it sent back really quickly. It says 0x. So this part here is basically a way of saying like, hey, this data or this data or whatever follows that follows is expressed in the hexadecimal. Expressed is maybe written is another way. Written using hexadecimal encoding, right? Okay. So right, so that's like a key that like, hey, these like 1, 2, 3, 4, 5, 6 characters that we've got. These you should take these, and if you want to translate it into another encoding like decimal, you should know that this data is like hex, right? So that's what 0x in Python and other places, basically, that's why you include it. It's like, hey, and the X is like X and hex, right? So it's like, okay, these are numbers that are written using hexadecimal encoding. Okay, so how do we go from, okay, so one thing you'll notice is that this number, so in hex, this number is a lot shorter, right? We saved kind of 2 characters we didn't have to send, but we communicated the same number. So maybe like a fun thing to do then is we can show, okay, how did that actually convert, right? So what's the relationship between, what's the relationship between a decimal number and a hex number? Well, let's see. I think easiest way is to go from hex to decimal. So typically what you do is, so each of these places, right, there were 16 things that could be, there were 16 different characters that could have been in this spot, right? It's really 15 0, right? So what you end up doing is you end up with if you want to actually convert it, you end up saying, okay, I'm gonna start it side. I'm gonna write this backwards because it's easier for me to count backwards. So what we're gonna do is we're gonna say, okay, this first one to move from hex to decimal, we're gonna take 4 times 10 to the 16, right? No, 16 to the 1. I think this is right. Hopefully I do this right. To 0 because it's in the first spot. So that's the 4 here. And then we're going to add to that and add to it C, which we all know is, if we look up here, we know C is 12, right? C really means 12 in numbers. So we can say that this is, well, I'll leave it as C times 16 to the first plus, which C is actually, well, I'll replace it. It's actually 12, right? So I'm going to translate that each character. 7 is just 7, still hexadecimal to the second, plus what was next? E. If we look up E, we can see up here that E is equal to 14. So you get 14 times 16. Can anyone guess what the next number is going to be? It's going to be 3, right? I lost my track. C, we're back at C, which is the number 12 times 16 to the 4th. And then the last one is 9, right? Times 16 to the 5th. So basically, if I write positions underneath these, this would be 0. This is position 1. This is position, R2, this is 3, this is 4, and this is 5, right? And these positions, this is just positions, right? I just started at the back and wrote 0, 1, 2, 3, 4, 5. These match up with the power that we raised that 16 to at each position. So the general formula to convert from any encoding to decimals, right? Because decimals are kind of the ones that like we're all native speakers of. So the general formula is the character value, so you have to go look this up, times the number of characters in that encoding, which was 16, right, for hex, raised, okay, this is kind of hard to read, times, so character value, which the character value times the number of characters in that encoding, raised to the power of the position of that character in the whole set, right? So the position of C was 1, so to figure out the C part, we would do 12 times 16 to the first power, right? And each one adds up. And that's because like each of these new characters, if you do this with decimals, basically each of these characters, right? So if we do the same thing with the decimals, right? So if we apply the same general formula that we came up with to these numbers, so I'm gonna 0, 1, oops, 0, 1, 2, 3, 4, 5, 6, 7, right? So if I wanted to write this out as a thing, it would be 8 times 10 to the 0. Notice that when you raise anything to power of 0, that's just makes it 1, right? So this is basically like saying the number 8. And then you would do 4 times 10 to the first would be what? So 4 times 10 is going to be 40, right? Here, I'll break these up so we can calculate each of these by line. So this is 8. This is what? This is 40. Then we would add 9 times 10 to the second is going to be 900, right? If I line these up, you'll be able to see this a lot nicer as it goes. Plus, what's the next one? 2, and I'm supposed to raise that to what power? The power of 3, which is gonna give me 2000, right? Plus, what's the next one? 8 times 10. This is in the 4th position now. So we have 8 now. Then we have 2 times 10 to the power of, where's 5? 5. So hopefully you kind of get a good idea of what's happening here, right? We're basically rebuilding this number here, but doing it one position at a time, right? And the 2 times 10 to the 6 is, I go back one. I know it's not 2, this is the number 0, right? So the 0, and then 1 times 10 to 7 gives me 1. Right. And so when I add all of these up, you can kind of see what happened here, right? If you add these all up, you end up with this number, right? Basically. Right. So those like add up each way. So basically when you're doing this, you're kind of redoing this process, except instead of using this base number of 10, so here, I'll rewrite this Indian thing that we did. This is like a lot easier to look at, right? So we did the exact same thing. Yeah. We did the exact same thing with the hex last time. Okay. So yeah, right. We did the exact same thing with the hex, except these numbers aren't going to look nearly as nice, right? So when I like actually start plugging these into Python, so I say 4 times, well, that's just going to be 4, right? It's just the number 4, right? Because 4 times this is 1, right? Secretly. It's 1. And then this is 12 times 16, right? So 12 times 16 is 192. Again, these don't look nearly as nice, right? 7 times 16 squared. 16 squared is 1792. What's 14 times 16 to the third is a big number. I'm not gonna write that down. Okay, let's see more. Sorry, this example is long, but it's cool. 16 to the 4. I get this number. Again, these don't look nearly as nice, right? Because we use like a different encoding or whatever. 16 to the 5. We get a big number, and then what should happen, hopefully I did this correctly. When I add all these up, I should get the same number here, right? So I can check my work. So I can add these all together, right? Okay, 4 plus 192 plus this number plus this number plus this number plus this number. Okay, moment of truth. Yeah, that's exactly the same number, right? So again, this is like a very long explanation of how how you can say the same thing, right, using hex versus decimal, right? Okay, so then, okay, so I think hopefully now we have like kind of a good understanding of like sort of what's going on with encodings here and a general idea of how they get made, like kind of what the formula is for these things, these numbers, and how you can translate basically between hex to decimal. Trying to decide if I want to like go through the process of figuring out how to convert from decimal to hex, right? So we just we took a hex number and we converted it to decimal. How would you take a decimal number and convert it to hex? And I think that it's something like, I think the process that you go through is you divide by 16, right? Oh, so first you divide by 1, I think. Mod 16. I think this is right. This is right. Am I going to mess this up? So I think if you divide it by, let's see, hang on. If I take this number and I divide by 16, I don't know if you guys want to watch me do this. It's fine. Yeah, no. That's not, I think you want to know how many times it divides by 16 though. Yes, perfect. Okay. So basically this is what this is if you divide this number by 16, what number do you have remainder, right? So if I divide, oh, this 0.25, right? Yeah, I think that makes sense. Lisa. Whereas if you do this to the second, right, what number do you end up with? 196 minus 4. Oh, okay. So what you do is okay, sorry. First you do it mod the number of characters. So this is converting from decimal to another encoding, right? First you mod it by the number of this. So you kind of see if we divide this by 16, how many are left over? There's 4 left over. Then we take this big number. So we've already gotten 4 out, right? So we already got 4 out. We already have 4 out. So now we're gonna subtract what we've removed from it, right? So now we take this number, I think, and we're going to mod by 16 squared, which will give me 192. 192 divided by, so that's the same number here, right? So we've managed to pull this out of it. Now I have to figure out how to convert this to 12 or to C, right? So if I divide by 16, what do I get? 12. Right. I feel like there might be a faster way of doing this, but like basically what I'm doing is I'm like pulling out every slot, right? I'm pulling out every slot, and then I'm converting it to the character that it should represent, right? So I pulled out the 4 by doing mod 16. So basically it's sort of the opposite of some of this. And then I subtracted it, and then I did the remainder and modded or divided by, figured out what the remainder is of once the, like, basically, if you remove this amount from it, what do you get? You get 192. So we're basically trying to isolate each of these like character spots. That sounds kind of weird. And then you subtract if there's anything left over. I might be doing this wrong. I don't know if this like generalizes, but yeah, you have to subtract out. So then I'd have to subtract 192 from this before I do the next spot. But there's an iterative process that you can go through here, and you can, yeah, so we just get this number, and then we would divide that by 92 divided by 16 the second to get 7. So that's the character that we would want, right? Okay, cool. So that's basically like how you would reverse engineer, go from decimals back out to hex. And I think there's a faster way. I'd have to like look it up, but cool. Okay, so now we know how to translate between hex and decimal, and let's talk a little bit about, so up here we had 2 encodings that we were talking about. Let's talk about some other encodings. So there's a couple other ones. The other one that's like extremely, what do you call it? You see pretty much everywhere in, well, don't see everywhere, but it's kind of like a very basic thing for computing stuff, is binary. The thing about binary is it only has 2 characters, right? So it's either a 0 or a 1. And so one thing we didn't really like talk about, and one thing I wanted to kind of like show you is like basically what happens when you get to the end of the character set, right? So the end of the character set here, I'm gonna delete those. So basically what happens when you get to the end of the character set, if you're counting up, right? So like in decimal, what happens after 9? Well, we can no longer send any more info in a single character. So now we need to send 2 characters. 2 characters. So after 9 in decimal, you'd have to send the number 10, right? So you'd send this. You'd send this 1, 0. Because we can't fit any more information in 9, but we want to say 1 more. So we add an extra kind of like slot, right? Okay, so binary is just a 0 and a 1, right? So there's only 2 characters here. 2 character set. This one was the 16 character set. I feel like you guys can tell where this is going. It's fine. Okay, so if I wanted to count to 10 in binary, we're just gonna start at 0, right? So we start at 0. And then maybe this, and then I say, okay, 1, right? So this would be in decimal. I'll keep a decimal running counter here as well. So this is also 0. This is also 1, right? And it's cool because like these, if you look at all of these different encodings, they all share the same character for the first like number part, right? Which is cool. So they share the same numbers, so 0 and 1, and all of these both mean the number 0 and the number 1. When we look at base 50, does base 58 change that? I don't know if base 58 does, but we can look at an encoding, which is a little bit different, which is kind of cool. Okay, so we're in binary here on the left, and we're in decimals here on the right. What happens when I want to say the number 2? Well, I have run out of characters, right? So given the way that we know that encodings work, once you've run out of characters, you literally just have to add another character to the front, right? So this is going to go back to 0, but we need more space, so to speak. So we're going to have to add an extra 1 at the front. Okay, so then if I want to say 3, that's fine. I can just keep iterating. I keep flipping. And when I'm doing this, I'm kind of imagining, like those digital clocks that have like the little faces that flip, right? binary only has 2. So when it ratchets up to what the second is, then the one next to it has to start flipping, right? And then the one on the bottom goes back to 0. And then you have to flip that one up again before you can flip the next one. But since there's only 2 characters, you flip them quite quickly, right? Okay. So this is 3. So what's going to happen for 4? Some great news. This is going to go there, right? So then if we wanted to go to 5, we would need 5, we can just do the here, right? So we start flipping back from the beginning. 6, this is gonna go to 0, but this is gonna flip up to 1. So we're basically like kind of repeating this section here, right? So this 0, 1, 1, 0, and then we'll go to 1, 1 without doing the top one again. R1, so this is 7, and then to get to 8, very exciting. 8 super. I'm gonna actually copy this one for reasons. 8. Now we have 4, right? So it's kind of cool. It's like, okay, you can ask the question. So this is binary. Look, this on the left is binary. This is just like flipping up furiously through the 2 characters that we have in this encoding set. Yeah, and so there's like 2 at every level, right? Because that's the number of, oh no, oh, then we get 4. There's 2 here, there's 2 here, and there's 4. Then there should be like 8 more. Anyways, before you start adding a new character. Anyways, cool thing that you start to see is that, oh, I said we go to 10. Sorry, I will, this is 9, and then 10 should be 10. Okay, so now we've finally flipped over characters on the decimal side too, right? On the decimals have finally had to add a new spot, new character, a new rune, I guess, as we call them. I don't want to get confused. So now I have 2 runes. It takes 4 like spaces, right? 4 like little pieces of information, like runes, I guess, as we'll call them. The same data that we could send with 2 in binary, in decimal. I'm sorry. So where was I going though? Oh, so there's a cool thing here about since this says binary, right? This is basically how many characters. So like at 2, there's you need 2 runes, right, to say it. Then at 4, you need 3 runes. And then, is that right? Am I counting right? I'm counting right. And then at 8, you need 4 runes. 4. So these are almost powers of 2, right? This is like a power of 2 minus 1. So like 2 to the second power is 4. 8 to the second power is 8 to the third power is 3. Anyways, okay. So it's kind of fun. There's definitely like the powers kind of like fall under here. It's fine. Okay, I might be. Okay, so right. So now we've learned like 1, 2, 3 different encodings. Cool. Okay, so now we know 3 different encodings. Let's look at a sort of fun other encoding. And that is introduced, I believe it was introduced by Satoshi in Bitcoin. In fact, we can go and let's go look at it. Let's go look at this encoding. I'm sure maybe you can guess what the name of the encoding is. Let's see. Okay. So I already have it open, but it's kind of fun to, why isn't this working? That'll work. Okay. So let's go to github.com. We will go to we go to Bitcoin. So we'll go to the Bitcoin repo. We can go into the Bitcoin actual like project, right? So this is all the code that is the source code of Bitcoin core node. Names are hard. And if we scroll down, they're alphabetical, which is great. We find one called base 58. Just on the way that, based on the way that, I don't know, code in words, based on the way that like C++ projects are organized, there's something called a header file. So this is the header file. And then there's also a CPP file. I don't actually write C++, but the C++ thing is like the actual thing. Anyways, this is the header. So this is the header for base 58. Satoshi wrote why base 58 instead of standard base 64. Actually, is it Satoshi who wrote this, or was it a different, it might have been a different person. We could look up who wrote this. I think base 58 was introduced after, well into it. But anyways, this is why base 58 is because we don't want, there's certain characters that they don't want. So they wanted to make it so that when you saw something written in the encoding base 58, if you're writing it down, they took out the characters that were easy to confuse. And so they said those characters, if you look at them here, they are actually, here, let me pull this up so it's bigger. These are actually hard to, these characters are kind of hard. If you saw them written, it would be confusing, right? This is the letters, lowercase letter L, uppercase letter I, uppercase letter O, and the number 0, like characters, right? Or like runes, as we've been calling them. So they took those out and they made a base, they made an encoding that they call base 58, that's character set doesn't include these characters. Okay. Okay, so cool. Like these are just basically, this is just like not very interesting. Let's go look at that other base file that we saw. There's 2 of them in here. Base 58.cpp. Okay. So here it has this thing right here. This PSBZ base 58 says all alpha numeric. So alpha is alphabet, right? Numerics, numbers, characters, which we've been calling runes, but kind of an interchangeable thing, except for, as we saw earlier, the number 0, the capital letter O, capital letter I, and underscore undercase L. So this is the set of characters that is in base 58. It turns out that if you take, so I'm gonna take this and I'm gonna add it to my set, right? So base 58 is this. Turns out, anyone want to guess how many characters there are in this series of alphanumeric characters I just pasted in here? I'll give you a hint. It's in the name of the encoding. Did you guess 58? That's right. You would be correct. There are 58 characters, right, in base 58. So let's do a little bit of like fun. Let's see. Let's take some numbers. Take some numbers in decimal and make them, write them encoded as base 58, right? That seems kind of cool. Okay, so let's see. If I wanted to say the number 1, okay. Why am I like making noises? That's because if you look at this, like kind of carefully, like so up here, all of these like character set we've been using for all the other encodings we've looked at up to this point, right, have included this character with the 0, right? But base 58 took it out. So if I wanted to, I'm gonna spread these out a little bit so they look like the other ones. I'm gonna stop there. Okay. So if I wanted to say like 0, I think this is how this works. I think if I wanted to say the letter 0, the number 0, right? If I wanted to say that in base 58 encoding, I would use this rune or this character, which is a 1, right? Whereas if I wanted to say that in, so if I wanted, here, I'll do this. So if I wanted to say it in base 58, it would be 1. If I wanted to say it in decimal, it would be 0. So, let me test this hypothesis out. So I have this Python package called base 58, which you can install on your own computer. using this, it's going to say you already have it, which is great. So then when I go into Python, I can say import base 58, and then I can say base 58 B58 encode the number. Does this work? Oh, we just want to do 0, right? No. It needs it. Hey. It needs to be the number 0. Oh no, it's Q. Oh, hey. Okay, something's going on here. Okay, so let's figure this out. I'm not entirely certain that I passed in the right, hang on. Oh no, we're getting into the like, Lisa has not tried this before. So if I do byte. I need to go look at the source code of this to figure out what's going on here. These are, I think, okay. This is like, I think what's going on here is that these are not ordered in the right order. Map base 58, 256. Hang on, let me go look up 58 Python. Base 58 encoding in Python. It is the same thing. Returns the number and decode S. Okay, we can just do this here. Decodes the string S into an integer. Encodes, returns a number in base. Okay, this is the one we want, I think. Let's get this. Okay. Oops. Something like that. Oh, didn't like that. Okay. Okay, well, let's see. Base 58, B58 encodes the number 4. Oh, import base 58. Modulo has B58. Why am I so confused? I'm gonna hang on. Get that here. Import base 58. Why am I struggling with this? Oh. It's working. Oh, okay. Yeah, it's the same thing. I'm not convinced that this is like okay, sorry. This should be the thing. It says so if we take, let me go back from here. So okay, it's telling me U, which is here, right? So I think what's happening is if you take the number 4, hang on, let's go. Okay, so now we're gonna get into even more wild things. Let's go ASCII print in Python. Okay. Yeah. Okay. So, okay, sorry. So my problem, what's going on here, it's printing out the letter U, right? And I'm like, okay, that's not That's not the 1, 2, 3, 4th character of the base 58 set. Why is it giving me the letter U? And this has to do with, there's another encoding thing called ASCII. Oh man, this is getting more complicated. Okay, but ASCII is basically, let me see if I can find an ASCII table. ASCII table. How do I share more? Okay. ASCII is basically a way of mapping actual characters in text. So let me see if I can find U to a value. Oh, it says it's decimal. This one's like, it says it's 117. Interesting. But basically in your computer, like the character that looks like an H has a decimal value. Oh, is it this one? No, none of these are making sense. That's fine. I don't know. This isn't hex. This is the value. But anyways, characters like in, so like this character has like a decimal value behind it. So what I'm doing is I'm like basically passing in a decimal value and it's like looking up where that decimal value is. This is hard to explain, but U is, and then so I can figure out, I can ask Python to tell me what that is. Oh, it is the 117. I did 4. Oh, that explains why I was confused. Okay. Sorry. So that basically when I type in, like when I type in this 4 here, this is the same as typing in the number 52, except I can't figure out how to give it to like, let it tell it to do the number 52. Let's try writing 52 in hex and see if it'll do that for me. So how do I get hex of 52? Is 0x34. We'll just do, if I do 0x34, will this let me, will this give me what I expect? No, okay, just kidding, cool. Sorry, I've usually used this with like other stuff, so this is like kind of new for me, but okay, anyways, let's go back to this. So when we type in this character 4, which Python tells us is an ordinal, no, not that, tells us has a value of 52. So basically we're saying, okay, what is the base 52 value of I'm sorry, what is the base 58 value of the decimal number 52? Probably should have just done this here. Okay, that's fine. So if I, hang on, I'm gonna get rid of these spaces so I can jump over. So if I go 52 spaces to the left, I end up with the character U. Okay, so this is really, this is working how I imagine, how I, what do you call it? Okay, so what am I trying to say? Okay, so let's do some decimal numbers and we will convert those to base 58. So this like thing is, oh, okay, so the decimal number 1 in, or the decimal number 0 in base 58 is going to be the number 1 because these line up here basically. So I'm going to go back to this because this is how I imagine. So if you wanted to say the number 0 in base 58, you would say, you would emit the character 1 basically. If you wanted to say in decimals the number, what, 45, but in base 58. So since this is beneath 58, we know that we can do it in a single character, right? But I'm gonna have to jump over. So I can go 45 to the left and I get the number n. So you could say that with n in base 58. How would we say this in hex? That's a great question. Let's do hex of 45 is 2d. I'm still sort of upset about this. It's fine. B58 encode. Oh, here's, okay, let's do it the other way. Let's do base 58 decode. So we want to decode the number 1, and I've been saying it's 0, right? Yeah. So it prints out the number 0. Oh, it's printing it out in hex. So if I do this as, so that's hex. So if I want to convert it to, if I do this, yeah, so that's the same number in hex. That's 0, right? So 0 in hex is obviously 0. And we already know this is in decimal. If I wanted to convert this to an integer though, I have to do this. So basically when you do this integer thing in Python, here, I'll put this in instead. I was giving it some characters. So I was saying, okay, I want to find the decimal. Int is basically a way of saying, give me the decimal value of this number, but this is the base that this number is written in. So you get 0, which is fine. So anyways, what this, Lisa, what this right here proves basically is that the value of this first character 1 is 0 in base 58, which is what we said. This is the exact same thing that we set up here, but I'm just showing you how you can get kind of the same result in Python. So if I wanted to say, okay, what is n, I would expect to get 2D out, right? Because it's going to print the answer in hex. So it this base 58 decode thing gives us the answer back in hexadecimal, which is fine. But that matches like our expectation that if we then take 2D and we translate that to an integer, 2D, there's 16 characters, it gives us 45, right? So there's like a bunch of different ways you can write the number 45 in hex. This is how you write in hex, and this is how you write it in base 58. Cool. Should we try to write, am I going to struggle with this? Should we try to write this number in base 58? Is this going to be, is this going to make me sad? I wonder if, what do I do? Sorry, hex of this number. Oh no. Hex
You can do base 58, B58 in code _int and then do it.
Underscore
in the chat.
Yeah. I think what I'm gonna do is I'm gonna do bytes. I'm gonna try this. At this point, but basically what I'm like struggling with is like how to make all these like different things tuck together. And then B58 encode X. Wow. So it says that in base 58, you would say that this is this. Which is kind of a weird thing. And then we can check our work by going backwards, right? So base 58, B58 decode of that is that in hex. That looks the same. That looks good. Okay, cool. Great. So my problem was that it wanted some encoding the input to this function. It wanted them in hex value, but in a special kind of like as bytes. Wow, that's really complicated. Should we like explain what that is? Because if we, let me explain exactly what that is, and then we can, I think this basically wraps up our like discussion of the difference between encodings and stuff. And I've got about half an hour to talk about. So we've talked about encodings. We've talked about base 58 and how you basically how base 58 is just an encoding that has 58 characters. One really weird thing about it is that that character set does not include the numbers, the number 0, the rune 0 that we're used to. So if you want to say 0 in base 58, you put a 1 in front of it. Fun fact to tie this back to Bitcoin. There's a type of address that either starts with a 1. So like signatures that are, what do you call it? Signatures that are public keys. Oh, not signatures. Addresses, Bitcoin addresses that are public keys. And if you're taking my class, we'll talk way more about this in detail. But addresses are public keys on mainnet. Always start with 1. Which is kind of like saying there's always start with like the value 0. Addresses that are like more complicated scripts on mainnet always start with 3. So what value is 3? A base 58 3 in decimal is going to be the number is going to be basically no, 3 is basically a 2. I don't know, sort of a random fact. Okay. Very random. In fact, kind of debating whether we should go look these up. That might be kind of fun. So if we go to like blockchain.info, we pick a random transaction. Oh no, this one's native SegWit. Okay, so this, oh, but it paid to, I think, it paid to a address. So all Bitcoin, well, not all, okay. There's different versions of addresses in Bitcoin. There's like a I usually call them like pre-SegWit. So like, okay, so how do encodings relate to Bitcoin? Great, I'm so glad you asked this question. Encodings in Bitcoin are basically, so encodings are basically used to encode information, which usually starts as hex values, which is why that Python library only wanted data in hex value, hex encoding, right? That was what I was struggling with. It wanted the Python library wanted my data to be represented as hex values, and I was trying to give it values as like something else, and it was like a different encoding, something called ASCII, and it was like barfing on me, but it's fine. Okay, so in Bitcoin, you take an address. An address is usually underneath the hood. It starts out as a series of hex values, like a hex string, basically. So it's a big hex number. You take that hex number and then you encode it in that same hex number, basically, and you re-encode it as base 58. And then the base 58 encoded version of the hex is what you send to your friend, right? So the actual like characters that you write on the page for a Bitcoin address. And I'm calling these like pre-SegWit, because post-SegWit or SegWit addresses use a different encoding called fetch 32. I bet you can guess how many characters are in that encoding. Give you a hint, it's in the number. Okay, but pre-SegWit, which we're just talking about pre-SegWit, because pre-SegWit addresses are the ones that we're using base 58. So pre-SegWit, the addresses are encoded in base 58. So this is an example of an address that's encoded in base 58. This one, it starts with a 3. So when I say, it starts with a 3, which if we where was it? I don't remember, I was writing that thing down, but as I was talking about earlier, so like if we wanted to, we could like, oh no, if we wanted to, we could take these numbers and we could take this string thing here, and we could figure out what each of the decimal values of each of these is, right? So 3 is 0, 1, 2. So this is actually a 2. This is a 2. 4 is probably a 3. We said earlier was something else, right? Okay, so you can kind of back out what these decimal values are of each of these characters. I'm not going to do that. Instead, what you would want to do if you wanted to figure out what the hex data that was actually encoded in this is you would go in here with your, first we would say address is bytes. No, address is equal to base 58, B58 decode. I just give it the stuff. So then we have address, and then I print that out as hex, and I get the same data as what was in here. So this is the exact same data, right? We've just taken it and we re-encoded the same, like, this is some very large number, right? In fact, now that we have it in hex, we can ask Python to tell me what number that is in hex. I mean, in decimals. Yeah, so this is the number. This is what that number is in decimal, basically. This isn't very useful though, right? Like, okay, who cares that this like number, like the fact that this is like this big number actually isn't what your computer cares about. Rather than like, how do I explain? Okay, so this is maybe a good entryway into like talking about endianness. So let's start talking about endianness, because in order to understand endianness, we need to introduce a new concept that's bytes. Okay, so we've been talking prior to this just in like pure numbers, right? So like, okay, like a number in decimals, and then a number, like how do you say that? Same number in hex, etc., right? Okay, so we've been talking about like plain numbers, right? So now we're going to introduce like a new concept, which I'm going to call number buckets. Okay, so number buckets. So basically, like, okay, so like let's go back to this. Like, okay, we just, and like in case you're wondering, like, where did I find this base 58 string from? It's just some random address from a random transaction I just happened to click on a block explorer, right? Block explorer basically shows you all the latest blocks that are on the Bitcoin chain. And this person spent some money and locked it all back up to this address. So I took the address and I was like, okay, this is a base 58 encoded string. Let's figure out what the hex is that this represents. And then we took that hex and we changed that hex. So this was the hex, right? Here. So this is like that same number as hex. And then this is that same number as like decimals, right? That we like actually recognize. But as like a number, this like isn't very useful. Okay, who cares that this like address was like this number here? One thing you can notice, right, to kind of totally an aside, is that these like lists of, in computer science, you call them a string, is basically like a list of characters like this. How this is like the longest one, right? And then they get shorter. And that's because the base 58 encoding is more compact, right? More compact. And the reason it's more compact is that there's more characters or like runes, right? More runes per like space, right? So you can, when you take the same like big number and you translate it to a more compact encoding, you end up with less, actually needing to like send less characters, right? Okay, cool. That's fine. Okay, back to this concept of bytes. Okay, so we have this big number, but this like big number is like not very useful. So instead of like, computers kind of have this idea of like a byte, and a byte is 8 bits. What is a bit? A bit is basically a binary space, like a binary character, right? So so this is saying 8 binary characters in a row is the amount of space we have in a byte. Okay, so what does that look like in binary? 1, 2, 3, 4, 5, 6, 7, 8, right? What is the biggest number that we can, so this is a binary, right? So this is in binary, this is the number 0. If we go back up, I'm gonna go back up to my, this count to 10 in binary. Oh, wow, that actually was pretty useful. Let's put it down here now. So instead of having it this, so this is basically like saying there's like a fixed number of these things. Go back. There's a fixed number of these things, and like, so just kind of imagine that these are like filled in right down to here. So what's the biggest? This is like a bucket, right? And it's a bucket. It's got a fixed number of like characters that it can fit, or like number of spaces that it has. There's only 8 of them in a byte. What's the biggest number that we can get in a byte, right? In decimal? That's gonna be, I'm gonna change all the zeros to 1. Oh, I'm gonna change all the zeros to 1, right? So this would be the biggest number you could do, biggest number you can fit in a bite-sized bucket. I'm laughing because I think that's kind of funny. Should we figure out what this is? Here, we can use Python, I think. Remember how when we were trying to figure out the integer, which integer just means basically like positive decimal number, not a decimal. Well, A positive number in decimal encoding that doesn't have any actual decimals in it. So like big positive numbers that like are round, whole numbers. Anyways, that's what an integer is. Told you I was assuming you don't know anything about computers. So yeah. And then so the second thing that you do is you tell how many encoding, like how many character encodings are there, like what encoding is this like string that you're telling this in, and it'll use that to figure out what the number is. Anyways, okay, so this is 255 in decimal. I really wish I could stop and take questions right now because I feel like I might be confused some people. I really hope not. Okay, right. So basically I passed in a decimal value to this integer function and it figured out what the decimal number is for me. It's 255. So the biggest number each byte can represent. Oh, here's a fun thing. Okay. Is 255, right? Okay. What is this in hex? So what is the exact same? What is the same thing in hex? Does anyone want to guess? Here's a fun fact. It's FF, which is cool, right? Okay, so why is this cool? Oops, with Python. So if I take FF and 16, I should get 255. Yes, cool. Okay, so why is this cool? What's really cool about this is that in hex, you can, so like in hex, you can express a single byte as always, like always as 2 characters, right? So every single value that is a byte, so there's 8 bits, right? So this goes from 0 to 255. That means in hex, you can express exactly the same numbers in 2 characters from 00 all the way up to FF, which is really cool. So this is why in computer stuff, when we're talking about like data and stuff, this is why usually it gets encoded or like printed out, like what you see is in hex values, is because those map really, really perfectly to a byte, which is, so 2 hex characters can express the same, like the same number of data as 8 binary characters, right? So a lot of time when you're dealing with like binary data over the wire, you can also write it in hex and it's like a lot more compact, right? So when I wanted to, if I want to give someone some data, like raw bit data, I can send them it to them encoded as hex, and then they can take that hex and decode it and they get back the byte value, right? So that was like, you saw me doing that earlier. I do bytes from hex. So let's do FF and we should get, that's not, the printout isn't very good. But basically when you do, so let's do FFFF because that'll just be, or here we'll do, why is that bytes from hex? So let's make it bigger, misspelled it, bytes from hex. So let's do FF00. So basically you'll see it buckets it. So it takes basically this like input that you did and it buckets it, it splits it up into bytes, which is 8 bits of data at a time, right? So the highest number that you can get in these bytes is 255, right? So it's basically taking this really long number here, this really, really long number, and splitting this up into buckets of the value of 255 each, basically, is what this is here. Yeah, so if I make this bytes from hex, yeah, I want to do bytes of hex, so this right here, this is basically, and basically this is be like a list of values. Can I do bytes? Duh, that doesn't do anything. That's like, okay, I wanted it to print it out a little bit differently. I'm not so like good with like Python to like know exactly how to make it print these out, is like, so there's a way you can take this and have it actually print its bucket value in decimal. And I'm not sure exactly how to do that for This is like, what if like B for B in bytes. If I do this. No. No. Okay, I did it. I'm very proud of myself. Okay, cool. So basically what we've done here, I'll make it bigger so you can see it, is I took this hex data here. So this is like the hex data that we had. Basically I converted that. So basically it like just split each of these two characters up. So each of these two characters is a byte, right? Which is 8 bits. So it basically does that. And so, you know, the X means in hex value and then the value. And so these are kind of just like splitting up, and then they get kind of weird because of that ASCII thing that I sort of mentioned earlier. Like what is this E8Z thing at the end? I don't know. It's not easy to look at or read, whatever. But then I was like, okay, I want to take each of these like buckets, right? Because we bucketed it all up, and I want to convert those into the decimal numbers so I can just like look at it, right? So we can just do a spot check here on the first two ones, right? So if you look back at if I look back at like this one, like here, the 0F, like so 0.5 and then 0F. If we remember from hex encoding to decimal encoding, like so a 5 in hex is definitely the number 5 in decimal. An F in hex is definitely the number 15 in decimal. I have no idea what this is. Here, we can look at here. 1C is the next bit. So I'm just looking at these two characters at a time, right? So 1C is basically 28. Okay, I believe it. That's 16. So this first one counts as 16, and then I think C was 12, right? Yeah, so 16 plus 12 is 28. Anyways, so basically, like this is just to say that like a series of like when you get like hex data, it's basically a bucket of numbers, and each of the buckets has been split into 255 like value of each one, and that's like kind of like all that this stuff is. Okay, so so those are bytes. That's how you get hex from bytes. That's how like hex you can get from base 58 to hex back to bytes then, basically by breaking the hex into like 2 character spots and then making each of those into a little bucket, and you can make a list of them. So basically you have a list of values, which is kind of cool. Okay, so those are what bytes are. It's a bucket. There's only 8 bits of information in there. So you can go from 0 to 255. Okay, so then let me remember. Okay, so then like, okay, so how does this pull into the topic that we wanted to talk about? I had to talk about bytes before we talk about endianness, but let's talk about endianness. So basically, endianness is like, okay, so if I take, how do I explain? If I take, let's see, let's just say, so this is our list, right? Let's just take, hang on, let me get it bigger. So the original thing was this, right? Copy it. I'm gonna paste it down here just to like repeat it. No, that didn't work. Okay, so just so we can see these right next to each other, right? So this was in hex, and then we split that into bytes, and we printed out the value of each byte bucket here. Okay, so what if, okay, so endianness basically means, so then if I take this number and I convert this into like a real number, oh man, I have like 10 minutes. I don't know how into like, but basically, so this makes a list, right? I'm gonna call it a BB. So that's just the same list. I saved it. So now I have it here. Like I just basically like stashed it. So I have it. So if I go through each element in this thing for like number in BB, I'm just gonna print it so you can kind of see what I'm doing. So for each number, I'm just gonna print it. So it just printed them out, one to like whatever, right? So it just prints them one at a time, goes through them. Okay, so if I do for number, okay, so let's say, so basically what I want to do is I want to convert this into a very big number, and I just want to show you kind of how that process works. It should, if we do it correctly, it should be the same as this very large number here, right? So I want to verify that I can convert this. Maybe I should do this a little smaller. Well, no, it's fine. It's the same process. Okay, so for for a number in BB. Oh, so I need like a sum, which start at 0, and then for index num in enumerate BB, I need to do, it's gonna be what? So it's gonna be, we printed out numbers, right? So it just prints out numbers. So I need number times, okay. So in bytes, right? So if we think about byte encoding, each byte was worth what? Was worth 256, right? So if I'm going to convert this to, oh man, we're using everything we've learned so far. This is cool. So if we're gonna, basically I'm gonna write a function that's gonna go through this list and it like basically do this, but instead of the 10, I need to use 256 here, right? 256, right? Okay. Because we're using byte encoding. Byte encoding, wow, that's another encoding we can add to our list. Where did our list go? Bytes, which are worth what? There's like 256 of them, which is cool. Okay. Okay, so for this and this, I'm gonna do, let me go back up to my formula. I wrote it down somewhere. Where did I write it down? Where's my like general formula is the character value, which we already know. It's a number times, so this is gonna be sum, and we're adding it up, so plus equals. Here, I'll just do it this way. So let's say the value is, so I'm looking on my thing, I'm looking right here. This is what I'm looking at. So first we're gonna take the character value, which is num, and then we're gonna multiply, so this is times the number of characters in the encoding, which we say for bytes is what, 256, and then raised to the power the position of the character in the whole set, right? So in this array that I'm going through, I'm gonna run out of time. This is terrible. Okay, it's fine. We'll keep going. Hopefully this just works the first time. So this index number basically tells me where in the array that I'm at. Am I gonna go through this backwards? Okay, it's fine. We'll figure it out. So then I'm gonna do this times index. Okay. And then I'm gonna take the sum and I'm gonna add whatever value with this row that we got. And so we're gonna go through the whole thing and we're gonna get a number, and our sum is not the right number, right? Oh man, this is great. We were looking for this number. We did not get this number, right? So something is wrong. And I'm gonna tell you that something that is wrong is that we need to go through our list backwards. So I need to reverse this list. I should show you what this does. I will in a second. I'm gonna do through, oh, I gotta reset sum to 0. Hang on. Okay. So this was our original list, right? If we go through this backwards, the other direction, so I just like putting a -1 like this basically prints the same list except backwards, right? So everyone see these are just the same list, but backwards. So we're gonna go through it backwards basically. So we're gonna do the same thing. We're gonna do, oh, and I gotta set sum back to 0 because sum right now is a very big number and I don't wanna add to it. So I'm gonna reset that to 0. So now we've reset to 0. We're gonna go back to the list again. We're gonna do the exact same thing. The only difference this time is that we're going back through it backwards, right? Okay, does that work? Yeah, check that out. Okay, we got the exact same number this way and this way. And okay, like, believe it or not, which direction are you going through the list is basically what Endianness is. All that Endianness means is, are we going backwards or are we going forwards when figuring out what the like decimal value of this is? And I could not honestly have like shown a better example of that, right? So we took basically the exact same byte list. One time we went through it and we started at the top one. So starting at the top one is actually called, the first time that we went through it, we started at they keep going up. Whoops, keep going up. We started at the so this was our string, right? I'm just gonna copy it again so you can see it and look at everything on the same page. So this is the hex string, right? So the first time that we did this, so every two of these characters is 1 byte, right? The first time that we went through here, we started with this byte and we said, okay, this is the smallest byte. So I'm going to take this small byte and I'm going to use the index of 0 and do 0 times to 256, so 1. So I'll take 5, and then I'm going to take this one, which is 16, right? Oh no, it's 15. So I'm going to take 15 times 256 because it's in the first position, right? So we started at the left. So this is actually called little endian. So the way that we went through it the first time, where we started at the side where the smallest value bytes are on the left, is called little endian. So smallest value bytes, right, on the left is also known as little endian. But that wasn't the right thing, right? Normally, most things, when you look at a number, and this is the same for decimal numbers, right? When you look at this decimal number, which of these decimal numbers, if you were to like break it out, kind of how we broke it out here, right? Which of these, like, remember how we like kind of broke this out? Which of these decimal numbers is the least value? It's this one on the right, right? This 8. This 8 is only worth 8, whereas this 1 right here is worth how much? This 1 is worth, I don't know how many million this is. It's worth this many, right? 10 million. So this character 1 here in this like set of numbers in this coding is worth 10 million, whereas the 8 in this thing is worth 8, right? So this is because the smallest value number is on the right side. This is called big endian. If we process this the other direction, which like you wouldn't because it doesn't really make sense, but if we change these around so that instead of this being times 7, we made this 0, we made this 1, we made this 2, 3, 4, 5, 6, and you go the other direction. Oh, that's not a 6. And this was 10 to the 7. So if we went this direction with these powers, so if we started basically at the other side, so if we did these but backwards, right? That would be the same. Basically, the way that you would call this then is because the smallest value like place is on the left side. That is what little endian is. And this has, again, like all that this means is that when you take data and you have hex data, it's kind of like which side do you start from to get a decimal value. And which side you start on really matters, as we saw here, because in one situation, when we started with little endian, we ended up with this number. And when we did it we did use the same data, right? But we processed it and converted it to a decimal number as big endian, which is how most things are written in like every computer thing. With the smallest values on the right, we ended up with a totally different number and the correct number as we were expecting, because most things process everything as big endian. Big endian means the small values are where you would expect them to be, which is all the way to the right side, not at the left. Cool. Okay. We are exactly at time, which is super exciting, but I'm gonna like, if anyone wants to hang over for 5 minutes, I can take 5 minutes of quick questions about anything we talked about or whatever. I don't know if there's a way. Hang on, let me see if I can see. How do I see all the people in my chat? Sorry, I'm like, this is like, no. Why is Zoom like this? I'm gonna stop sharing. Maybe that'll help. Cool. Oh, there's a chat going on. Wow. Okay. How can you tell if a number is base 58 or not from CAM? That's a great question. You can't unless someone tells you that they're using that encoding. So remember how like the very beginning we talked about how very beginning we talked about like there's some information we want to share and it requires this shared understanding of the encoding that's being used. That's like pretty much true, right? And also like that goes the same for little Indian versus big Indian, right? If you see a string like a hex string, so a hex string is just basically like a whole bunch of hex, right? String is just like a bunch of numbers and stuff all together. That's a string. If you see like a hex string and no one has told you what the endianness is, like remember when we like went through it and we added them all together, etc. No one's told us what the endiness of that is. We don't know which is the right one unless someone tells you. So yeah, so you kind of need someone to let you know what the data is encoded in order to be able to decode it correctly. And that's just kind of how information stuff works. Like if someone sends you a message in Spanish, if you don't know it's in Spanish, you like kind of need to know that it's in Spanish to decode it. And encoding works the same way. Okay, where does endianness come into play in Bitcoin from pre-req? The answer is that it comes into play in transactions. So the class that I'm teaching is a transactions encode, like basically we're going to learn everything there is to know about Bitcoin transactions at the byte level, like basically protocols. It's a protocol class. So we're talking about what is in the message that is a Bitcoin transaction. And it turns out there's a bunch of hex data in this, and some of the hex data is written, some of the fields of hex data are written in big Indian, and some of them are written in little Indian. So you have to know, and like actually the earlier question was a great question for this. Like you kind of have to know, like that's why we're taking the class. You have to know which of those fields are in little Indian and should be decoded using little Indian decoding versus big Indian and decoded using big Indian decoding. Because if you use the wrong big versus little, you'll end up with like completely the wrong result, as we saw. So that's cool. So does anything use little Indian? The answer is yes. A lot of the Bitcoin transaction uses little Indian. And why would they use a mix of big and little Indian? This is also a great question. This is a great mystery. No one knows. Satoshi is the one who developed the Bitcoin transaction format, and we can't change it because it's like the way that nodes all communicate with each other because they all understand what the Bitcoin transaction looks like. Yeah. So yes. What do you call it? The I don't know. No one knows why you mix big and little Indian. And Satoshi did not stick around to ask stuff. Let us ask questions. Okay, I'm scrolling back through stuff. Is there any more questions? I don't see any more questions in the chat. Sorry, I'm scrolling back. I was not paying attention to your chat. Oh, someone figured it out. New message. Okay, great. Okay, cool. Well, I'm gonna end it here. We're like 4 minutes over. Thanks everyone for coming. I will put up a, what do you call it? Recording later after the fact. Great. And for those of you who are in class in 2 weeks, I look forward to hanging out and doing a lot more of this with y'all for the next six weeks and stuff. Okay, bye everyone. And meeting for everyone.